So, good afternoon, everybody. This basically is a repetition of the presentation I gave yesterday. It's a technical part of 2110. It's about synchronization and alignment. So if you do not want to be disturbed by the noise, just go there and get your headphones. They are really nice, isolating the noise coming over, and might help you to better understand what's going on. So I see some of you, so a quick introduction. My name is Andreas Hildebrand. I'm working for ALC Networks out of Munich, and ALC Network has invented the Ravenna audio over IP technology. And this presentation now is about, well, synchronization and timing. So before we jump into the topic and explaining how synchronization and timing in 2110 is achieved, we have to look at the requirements. What are the requirements we want to fulfill with any transport scheme like AES67 or ST2110? So we definitely want to have media bit transparency. So that means any audio, any video signal we are feeding into the system should be capable of leaving the system on the other side with any bit unchanged. So that means for audio, we are not allowed to do any sample rate conversion. So whenever we have mismatch of clock frequencies, we would have to do sample rate conversion, and this is something we definitely do want to avoid. That definitely means that all the streams in the system have to run on an identical media clock. And by identical, I mean, you know, if we say we are running on 48 kilohertz, I mean the exact same 48 kilohertz and not just 48 kilohertz, right? So then if we have a network, we definitely want to be able to transport streams with any media clock concurrently on a network. So we don't want to switch the whole network to operate on 48 kilohertz or on 44.1 or 96. We want to be able to pass streams with 48 kilohertz as well as with 44.1 or 96 around on the same network at the same time. It doesn't mean that the receiver is able of receiving 48 and 44.1 kilohertz streams at the same time, but there may be receivers which are receiving 48 and others 44.1. And so the network should be capable of transporting this at the same time. Well, with a professional approach, we definitely want to have a determinable end-to-end latency. So that means we definitely want to know if we squeeze something into the network, we want to have an exact time when we can get it out again. So not about 10 milliseconds or as soon as we have it, or maybe 12 milliseconds this time, and if I next set up the system, it's 5 milliseconds. We want to be able to absolutely determine the link offset, the latency through the system. And of course, we want to have a low latency, right? We want to be able to do less than 10 milliseconds for sure, and if possible, even less than maybe a millisecond or something like that, depending on the requirements. So, determinable latency. And also what we want to have is a time alignment between streams. Just guess if we were sending out a stereo signal as two individual streams on the network, and we have two speakers. We definitely want those speakers to play out the streams at the very same time, so sample accurately, right? We don't want to have a shift or maybe even an ongoing shift. And then, of course, nobody needs that green house clock cable anymore once we have the network in place. So it should be capable of just working as a clock reference, even without any stream going on a network. So from those requirements, we have some consequences. That first consequence is, with all these requirements, we can't do any clock reassembly by looking at any incoming stream. That's the traditional way of RTP streaming. We receive a stream, we look at the stream, and start to adjust our media playout clock according to the incoming packets. So we adjust once the clock is too fast, we are running out of buffer, we slow down the clock, the buffer builds up. Once the buffer builds up too fast, we are increasing the clock again. This is something which does not work because we now have multiple streams at the same time on a network at the same clock. So distribution of master clock beats, so just frequency distribution, is also not enough because we want to have exact time-wise alignment. So that is not sufficient. We need to have absolute common understanding of time by all participating devices in the system. So what we do have to do is distribute time on the system instead of just clocks or instead of doing nothing at all. All right, so with what accuracy we would have to distribute time? What is the accuracy requirement we need to achieve? Let's look at the audio application, which typically have the highest accuracy requirements of all media applications. We definitely want to be able to sample accurately aligned streams. So the left and the right speaker play out the very same sample with respect to time in time. That means we need to have a time precision which is as accurate as plus minus half a sample. So both speakers need to have the same time with a deviation which is not larger than plus minus half the sample period, which at 48 kilohertz is plus minus 10 microsecond. A 48 kilohertz sample period is something like 20 plus microseconds. So if we want to make sure that every speaker is playing out the same sample at the very same time, it has to have plus minus 10 microsecond maximum deviation. And if we increase the media clock frequency, well, the maximum allowed deviations decrease accordingly. Now that is sample accuracy on playout, but I was asking for clock reference distribution, so we should be able to have a time precision which would allow us to generate media clocks on the local devices with a precision which is required by AES11, which is a standard for which says the maximum deviation for clock jitter and wonder is plus minus 5% of the clock period. So that translates into even tighter numbers. So at 48 kilohertz, we need a precision of plus minus 1 microsecond. And if we operate at 192 kilohertz, the precision needs to be down to 250 nanoseconds. So how can we achieve this? Well, in AES67 and 2110, using the same mechanisms, we have all nodes running a local clock. And by clock, I mean really a clock which is aware of time and not just about frequency. And these clocks are synchronized to the common reference clock in the network, we call them the wall clock, through the PTP Protocol, Precision Time Protocol. This is an industry standard which has been invented in 2002 as the version 1, and then they had a rework of this in 2008 and they called it version 2. Unfortunately, there's no backward compatibility. So you have to either use version 1 or version 2. And well, of course we use version 2 because it offers more precision and more flexibility, particularly in larger networks. So 2110 and AES67 settled on PTP version 2. Now, when we have time, absolute time, in our nodes, in our individual nodes, we can tell the nodes to generate any desired media clock we want them to generate, because time and frequency is a direct relationship, right? So all the nodes produce or generate their media clocks independently from their local clocks, which have a precise synchronization with the master clock. So here's an illustration how that works. We have a master clock instance on the system, which might be referenced to GPS, particularly useful if you have to have the same synchronization in various spaces, in various regions, but it's not a necessary requirement. We have to have a master clock instance on the network. That's distributing the time to all the individual clocks in the devices. So every device is a slave clock, and PTP is the protocol which distributes the time and makes sure that the precision requirements can be met. Now, since every node is on the very same time scale, has the very same time, they can generate their required media clocks independently. And if we look at these media clocks on an oscilloscope, we would actually see that the frequency as well as the phase of the clocks is very accurately, and depending on the network structure, traffic and so on, it can definitely match the requirements of AES11, plus minus 5% of the clock period. So that's the way media clocks are generated. Now, since we have the absolute time, any desired media clock can actually be generated. So if a node has the capability to be configured to 48 or 44.1 or 192 kilohertz, it can just generate this clock, and any of the other clocks or nodes can be configured to have the same media clock if they support it. It's not required that anything else than 48 kilohertz is actually generated, but most devices offer 44.1 up to at least 96 or 192 kilohertz per configuration. Now, this makes clear that we now have concurrent operation of streams with different media clocks on the same network, because the network just doesn't care. It's a matter of the configuration of the individual node to which media clock it is set or working on. Phase accuracy, as I said, can be met, particularly in larger networks that might require the deployment of PTP-aware switches. PTP-aware switches are those switches which can identify PTP packets, so these time packets, on their incoming ports, and they may regenerate the time on their outgoing ports, that's the boundary clock, or they can measure the resident time inside the switch for such a PTP message and correcting their hold-up time, their residential time, when they are sending out the packet again, so that the downstream node has an exact measurement what the time, including the jitter offset or the hold-up offset, had been, and can correct and adjust its individual clock. I'm not going into the mechanisms of PTP here, because that would be another presentation, but just take it for granted the PTP protocol can cover with these cases and can generate precisions down into the dual-digit nanoseconds range. Okay, if you have to, as I just mentioned, synchronize different facilities in different regions, use GPS as the reference. You have local grandmasters reference to GPS, because GPS is the most accurate, common, universal wall clock we have. The GPS system can have precision down into the picoseconds range, actually. Sounds totally amazing, but it's actually the case. Now, the secret with all the further requirements we have is now when a node is taking in a sample, either from the AD converter or from the sampling stage, it exactly knows at which time it has sampled that particular media information. So with every, let's say, falling clock period or leading clock period, it has the exact time of that clock period. So every sample which is taken has an exact time with reference to the wall clock. And since all the nodes are on the very same time scale, if two independent microphones would sample the very same acoustic event, they would actually have the very same timestamp on that sample, right? That's the secret, how we can actually relate things to each other. And here's an illustration coming up how that actually works in the system. To fully understand this, we have to introduce 3 clocks to the system. The first one I've already mentioned, that's the wall clock. And a local copy of the wall clock is living inside the nodes, right? That's the copy of the wall clock inside the nodes. Then we have the media clock. This is something which can be set to 48 kilohertz, 44 kilohertz, whatever. That media clock is derived from the local clock, which in turn is referenced to the wall clock. So we have seen that all these clocks are identical. And now the third clock in the system is the RTP stream clock. That's actually the clock which is driving the stream across the network. And that is individual per stream. Now the good thing is that with linear audio, with L24 audio, the standard says this RTP stream clock has to be a media clock counter. And I'll come up to this in a moment. I just want to illustrate this 3 clock approach in an implementation. So we have a sender and a receiver. We have the reference clock, the wall clock, the PTP master. We have local clocks in the sender and the receiver, and that local clock is synchronized through PTP. First stage. Second stage is there's the media clock. That media clock is producing any desired, well, frequency, media sampling frequency, but it's directly related back to the local clock. So that means the receiver has the very same principle. Its media clock, if it's set to be the same sampling clock or media clock, is absolutely the same media clock. So we have 2 independently generated but absolutely identical media clocks, right? So now the stream comes into game. Whenever there is a stream coming from the sender, that has its own RTP clock. That's the way the RTP protocol works and the way it transports content. And as we have seen earlier, the RTP clock has a direct relationship to the media clock because it's a sample clock counter. Now the standard, which is the RFC3550, a standard which is more than 20 years old, I guess by now, is calling for a media clock counter and a random offset to its referring media clock. So in other words, if I set up the stream, I add a random offset to this clock counter, and the reason is the RFC guys thought, okay, if we go with encrypted audio streams, and we would have a known value inside the encrypted section of the packet, that's a perfect hook for decrypting that packet without authorization. So they have a strong recommendation in that every stream has a different random offset. Well, of course, the receiver, upon reception, needs to know that offset, right? Otherwise, it just doesn't know, okay, what is the time the sample had been instantiated? And that is the offset is transported from the sender to the receiver out of band. So it's not part of the RTP protocol, it's part of the SDP protocol, Session Description Protocol. So we have two different protocol layers, and this random offset information is transported on a different link or a different connection between sender and receiver. So it does not threaten the encrypted data of the RTP stream. So that's the way the RFC3550 works and AES67 works. Now 2110 came into game, and when they looked at this, they said, why would we bother about this random offset? Why would we bother about security and deciphering and so on? We are in a closed environment anyway. We don't care. Let's make things easy. So they require that this offset must be 0 for every stream generated. So every receiver has to directly put the number of media clock counts into their timestamp field. Actually, on the network, that means that any stream is directly related back to the master clock, not just in a relationship, but also in absolute value. So all the streams, from the perspective of the sampling of the timestamps, look absolutely identical, as if that particular stream would have been started at the origin of time, at the 1st January of 1970. That's not the origin of time, but it's the origin of PTP time, which serves International Atomic Time, TAI. So we have the 0 offset in there, and AES67 devices which want to play in a 2110 environment need to respect this, because the 2110 receivers most probably are not able to cope with the random offset. Just as a background information. Here's how this looks like. RTP packet. We have an RTP header which carries vital information about the RTP packet. We have the payload area. That's where the naked audio data is stored, the L24 audio data. And inside the header, there's the timestamp field. That is 32 bits in the timestamp field, and we know by now it's a media clock counter, right? So anybody has a clue what that counter should carry, what number that counter should carry, if we assume that the stream has been started at the 1st January of 1970 and is running at 48 kilohertz? Does anybody have a number for me? I don't even have that number, because I know that at 48 kilohertz, this field is overflowing once per day, roughly. So if you count 48 kilohertz cycles, they will use all the 32 bits roughly once per day. Well, that somehow seems to break the possibility to identify when a sample actually has been instantiated, has been generated, right? Well, in a file storage environment, yes, but remember, we are in a real-time streaming environment. So whenever I instantiate a stream and sample an audio event, an audio sample, and transport is on the network, so how long would it take before a receiver actually would receive it and decode it? More than a day? Probably when it's going to Alpha Centauri and back, but that's not the case yet. So we are still between generation and reception, within a day. So, and by doing a simple modulo 32 calculation, we can exactly determine when that sample, the first sample in the payload package, that's what's indicated in the timestamp, has been instantiated. So the receiver is perfectly clear on when a particular sample, upon its reception, has been generated by that sender by looking at the timestamp field, even if it's just a 32-bit clock counter field. So that's the secret behind the whole timing of 2110 and the synchronization. And now it's clear that if I have the absolute time when a sample has been instantiated, I can dial in any desired or required delay for when it has to be played out. I can exactly say, okay, I want to have an exact determinal playout of 3 milliseconds after that sample had been instantiated by just adding 3 milliseconds in clock cycle counters to the timestamp field of the incoming RTP field, comparing it against my own time, and delaying it for the further delay. It has to be delayed in order to exactly match the T0 plus 3 millisecond playout time, because both are in the same time, right? So that's a determinable way to play this out. Here's a diagram taken from AES67 describing this. We have the ADC, or the input stage, with the sampling reference point. Then everything is done through packetizing this and transporting it, depacketizing it, and the whole time which passed since then, where the sample can be presented to the egress, to the output stage, is what we call the link offset. So if we have a link offset of 3 milliseconds, for example, a desired one or a dialed in one, and the sample arrived at the output stage after 2.5 milliseconds of its generation on the sender side, well, the receiver knows it has to buffer that sample for another half millisecond before it can play it out exactly. And we have these exact times. Remember, times are down into the nanoseconds range. That's the way how we have the determinable link offset, the determinal timing in the system. And now it's clear if we want to reference or align two independent streams with each other to have a sample accurate playout from independent streams, even from independent devices in the network, we just have to look at the timestamps. We have to dial in the same delay for those devices. So left and right speaker do have to have the same delay configuration, always with respect of the generation point in time. And once they have the same delay configuration, they will make sure, through the process explained earlier, that any incoming sample has the same playout time. And that works through the whole system, not just within one device, because they are all on the very same time scale. Understood? Right, so then we come to the practical application of this. Let's look at a typical production workflow in a typical video studio. We have a camera that sources some video frames, processing devices in between, and finally we have a viewer which visualizes the video content, right? So we have some processing stages and a bit of a link delay in between. And we have an audio source, a microphone. We have, let's say, one mixer in between, and then we have the speaker. And we definitely want to align the output of the frame, of the video frame, with the audio sample. Now, from this example, it's clear that the audio passes through the network much faster than the video. So we need to hold up the audio playout for a certain amount of time in order to match the playout of the video. Essentially, the link offset delay from video and audio path just have to be the same, right? So we have the buffer, and any incoming audio samples need to be held up by that device in order to match the configured playout delay. To have lip sync or whatever for whatever reason you want to have that alignment between the streams. Actually, in IP, every device has these buffers. They have to have these buffers because they have to cope with jitter buffer originating from the network. So whenever they want to process some incoming information, they have to de-jitter. Any potential jitter packets have been built up on their way through the network. So every IP device has this input buffer. It's just a matter of how large they are. That's a matter of implementation at the end. Okay, so now we are facing a severe problem. If you followed me along, we have one stream original audio and one stream original video. That is being received by the subsequent processing stages. The audio or the video is extracted, is processed, and once it's processed, it's packed into a new stream. and of course it receives the time at which it has been thrown into that packet onto the network. So the original time is lost, right? So what are we going to do with that then? So here's the problem again, what I just described. So we have several possible solutions to cope with that. Some are suggesting, okay, why not use the original timestamps then? So store the original, the original timestamp of an incoming packet, let the packet and the sample being processed, and then reapply that original timestamp. Well, that could work, but under very, very constrained circumstances, and it has a consequence. It follows lots of problems with that if you have to go through many of these subsequent stages. So at one certain point in time, it can overload buffers. You need larger buffer requirements, and then also, how does the processing device know about the exact processing time inside? There are a lot of problems. Besides that, it's contrary to the RFC 3550, why you not want to do this. The second solution is we carry the original timestamp of the original essence timestamp as in-band metadata. In-band metadata means we generate a new stream, use a new timestamp as per RFC 3550, but add the original timestamp as metadata into the payload format or into the RTP packet at some area. Now that poses another area of problems. Either you would require a new payload format, because RTP for linear audio, there has the L24, and in the L24 there is just no space for timestamps. It's just raw audio data in there. So you could use the RTP header extension mechanism. Well, unfortunately, that's just an experimental a portion of the RFC 3550, and explicitly states it should not be used for regular applications and payloads. And plus, if you have RTP header extensions, it gets difficult for receivers to actually cope with these header extensions, and they can grow, because some see only the timestamps as a header extension, and others see other metadata which they want to insert into the header extensions, which in turn would decrease the payload area, because we have a maximum packet size which we can transport. So that is a way which could work, but it's also not a very recommended way. And then the third option is we carry the origin metadata, timestamp as out-of-band metadata. So in other words, we'll record the origination timestamp of a media essence and keep that away from the whole streaming process. Keep that somehow in a database or pass it along as an out-of-band information, as a separate stream. And actually we have several of these approaches currently going on. X242 AES is an audio metadata stream definition. We have 2110 has work on the -41 document, which is fast metadata streaming. And we have NMOS specifications, which also pose the possibility of coping with any sort of metadata information related to media streaming. But nothing has been fixed yet. I'm just mentioning 3 various possibilities. Some have some drawbacks and others are not yet available. So what are we going to do right now with it? Because we are building facilities and we want synchronization, right? So the current intermediate, maybe it's not so intermediate, maybe it's even a persistent solution, is that we leave the alignment task on the ends of the media essence processing chains to the management layer, which typically is a broadcast control system of some kind. And even if it's our broadcast control system on top of us all. So in other words, devices report their processing delays to the broadcast controller, and the broadcast controller then knows how many stages, how many different processing stages an SN flow passes through, and then accumulates that and tells the participating receiving devices, oh, you have to delay your playout with respect to the incoming stream from the last processing stage by half a millisecond or 1 millisecond or 30 milliseconds, and can exactly calculate that for any end point for that particular media essence. So here's the picture again, which we had for that application. And what happens is we add a broadcast controller. devices reporting their processing delays, so to say. Of course, what is missing here, the green arrows of the devices also reporting their origination timestamp. That's actually missing here in the diagram. And then the broadcast controller cannot just configure the individual delay buffers, but it also can, most importantly, configure the end buffers on the processing chains, making perfect alignments possible. Well, and if we don't have the broadcast controller, the most easiest way to have perfect alignment of the audio with a video frame, lip sync, is looking at the picture, listening to the audio, and dialing the configuration up. Oh, we need a bit more of delay. And once it's set, it stays there for all the time. It's determinable. It doesn't change, even if you set up the stream again. So that's the way the whole synchronization and timing works in 2110. We can see that for a fully working system, particularly for automatically working system, some more work is required, but that work is already going on. And for now, that is certainly not a reason to refrain from deploying IP-based solutions, because there are working schemes which cope with these peculiarities right now. So this was a very deep technical session. If there are any questions, I'm already 2 minutes over, and I see Ken waiting there, but if there's a question, I'm happy to answer that. Any questions? So the question was, if I have multiple streams, basically one stream would be the quote master stream, which all the others have to be synced to. Yes, in this case, it would be not the master stream, but the master chain, which has the longest delay. So if you want an alignment, you always have to follow the longest delay in the chain, the stream with the longest delay. That is absolutely clear, that's correct. Okay, I guess that's it. Thank you for your attention. I know this is a very deep technical topic. If you have any further questions, I'm here. And